Here we go. So, let's see. Last several times, we have been talking about asynchronous design. Okay? And we ended up talking about a style, primitive variables. We named the states, letters, or I don't care, you could use words or whatever. It's just not the number pattern. We tried to find the smallest number of states, and then we looked at our design to see if there were, critical races particularly, but anything else we want to remove that would be dangerous. And then we picked an assignment like one hot or gray code to actually assign numbers to those states. And I pretty much left it there. So this is just a comment to you. I left it there because at that point, it is trivial, right? Now you have gone back to combinational logic design. So you've basically got a table for gray code, and so you can just implement. If you want to use a latch, then you'll take, your design for your SR latch and get, find out whatever you're going to need, S and R, that's going to go into it. You do your design, you get your outputs SR. You're basically building that next state logic. That's what that table contains. If you're doing non-latch design, then you're going to get what your next state is, and that feeds back to what's going to come in as, what the current state is to then get the next state again. And so you'll have a feedback wire if you don't use the SR style latches. So once you have that table, you're basically done. It goes back to first course in digital logic. How do you solve it? I would generally recommend Carnot maps, or if the design gets a little big, then using, Klein-Mikulski or Espresso or, some other reasonable logic design that's going to get the overlapping states so that you don't get the problems, right? And everybody, like when I say making sure you have the overlapping states, everybody remembers what the problem is with, say, for instance, lookup tables or other styles of logic that can introduce problems. Is that a yes or a no? I'm getting like one or two and a whole bunch of cases. So really quickly, right? Let's just do a small world's smallest design, right? Or as small as is reasonable to do. I got two variables. Let's even just say I've got something pathetically simple like this. If I'm doing a Carnot map, I'll do that with evidently the blue pen, right? A K-map is going to find the biggest encirclement, right? So if I was going from, A equals 0 to A equals 1 in this spot, I'd be doing this transition, starting here, going to here. It's 1 the entire way, right? That gate always stays on, no problems, yay, right? If, on the other hand, next pen, evidently red, if I was doing a lookup table or a bunch of other designs, what they do to make muxes do this too. Tons of designs implicitly handle this because they switch at the smallest units. So they're in essence doing the tiniest encirclement possible, right? Because that's how, if you think about, like, for instance, on a mux, all right, 0, 1, 2, 3, right? To pick them, right? Here's my mux. Well, how does it handle these? Well, for 0, it's checking to see I've got 2 address bits coming in. Right? Let's say address. Oh my gosh, wow. Address 1, address 0, right? Most significant, least significant. What happens for this particular bit is I've got the wire coming in, and I'm going to AND it with the negation of A1 and A0. All right? So if A1 and A0 are both 0, they'll both be 1. All right? And let's just call this X. right, and call this y, then y is equal to x ANDed with, right, this, and technically it's another big and, but I'm just going to separate a prime and a0 prime. So if both of these are zeros, when they're prime, they become 1. Right, so this whole thing becomes a 1 if a1 equals a0 equals 0. Right? So if I'm at position 0, right, both of those are 0, this becomes a 1. X and 1 is x. Yeah. So under this condition, y gets x. That's all x gets. All they do is that's what x is. It's a whole bunch of these gates. So for the first one, for 0, you both negated. For 1, I want the 0 and negate the a1, and I don't negate the a0 coming into the AND gate. The second one. There's just a whole bunch of AND gates together that does that. But that means implicitly each of those AND gates only turns on under those conditions. It is a tiny encirclement. It's the encirclement of just that box. Which means if I'm switching on one of these, right? Here in this position, when I'm going from here to here, since it's a tiny encirclement, it sees a 1 first and then a 0 and then a 1, so you get a glitch. Right? So the multiplexer is going to insert glitches all over the dang place. If you're over a timing system, who cares? Right? But if you're anything, you have time. So you can mechanic. I don't want the glitches. The same thing is going to happen if I do a lookup table memory, because implicitly memory is doing the same thing, check each address. And so it's also going to have this exact type of a problem that's going on. Does that make sense? So the only one that avoids this is when you do a maximal experiment, and that only happens with a moment, applying the Kluski, or we did the algebraic version of Carmichael map, right? Or espresso, which is the fast heuristic method to do find the Kluski. Right? All of those do maximal encirclements, right? Which means no glitch. You basically want a glitch-free design if you're doing async. Right? Because anything will trip you up. We worry about all kinds of stuff, so we worry about glitches. You don't have a clock to remove, which is our common cheap way of removing things, allowing us to access these other kind of cool, easy techniques. The cool, easy techniques are off the table when you're doing async design. Because otherwise, it's going to be glitchy. Glitchy async equals doesn't work. So just remember, you have to, when you do async design, do the careful one. And I would even include the extra encirclements so you don't get glitches in between other ones. Right, remember, if you have, just to make sure everybody remembers this one, let's go up one size. All right, so I have A, B, C, right, and imagine I have something like this. I don't care what your encirclement is. There are two different ways you can do it. There's the basic one, which covers these. Everything I want is covered. And then I said there is the safety feature where you add in this one. If you are dealing with async, you want that extra blue encirclement. And the reason is if you don't, when you do this transition here, you are going to go from green on to both off to the other green on. Whereas if you have the blue, there's something maintaining it staying on, so you don't get that momentary drop in between. So just saying, whenever you're doing async, be paranoid. Right? Because remember, just because you're paranoid doesn't mean it's not out to get you. And in this case, async is just dangerous. It's always out to get you. So just be careful. Yes? But once we have those primitive states and we've assigned things to them, basically you're just down to do your encircling statement design. Good? Okay. So, cross that one off. We're gonna now get back to kind of what our next thing is, which is dealing largely with timing. So this is semi a new thing and semi not. This is actually applicable to all logical stuff we've got. Right? What we're caring about is how do I know how long it's going to take for something to happen? We have to do this for synchronous designs to get a correct clock, but with async, we still worry about how long can it take to update things. So no matter what you are doing, you do care about timing. So the question is, how do we measure the timing on things? I'm going to do this from the context of a time circuit because, again, 99 point something percent of the time you're dealing with a time circuit. And it's not that different from the known time. So let's go to our basic design area of what we're doing when we're dealing with some type of a sequential logic. So remember, we have two big categories, combinational logic and sequential logic. And sequential logic can be synchronous or it can be asynchronous. So we really kind of have three different areas we're dealing with. Okay? Combinational, what is combinational logic? Determine the outputs, right? If the outputs are determined by the inputs, then it doesn't matter what the current state of the system is, does it? Which, if there's no state of the current system, there's no memory. That's the other way of thinking of combinational logic. There is no memory. So therefore, the outputs, there's only the inputs to determine them. So they are equivalent ideas. So just remember, when we say that, we often do like to, and that's where the name comes from, to say the outputs are a combination of the inputs, and you just think in your head, therefore no memory. Okay? Oh. All right, so this, in any of our designs, is combinational. And we have inputs and we have outputs. We can also add in, and usually do, have memory. Right? And this is only memory units. This could be synchronous memory units, this could be asynchronous memory units, whatever, right? This could be Ps, this could be RSs, this could be JKs, this could be Ts. Right? These are 4 types of memory we use. Anybody give me a quick rundown of what each one is? What's RS? We just did it, right? That and reset. Right? The next easiest one, and we did use these ones briefly, what's a D? The data you want to store. The input, you put the data on it, and it's as simple as just putting an inverter between R and S, so that in essence you force it to whatever you put in is the value to store. What's a T? Toggle, right? Whatever it is, you get the opposite of that. So you can kind of think of it as putting a negation when you're dealing or technically you're doing an XOR, feeding your state back an exclusive orient with your data coming in. All right, so what it does is if the current state is on and your data is 1, it'll flip it. So in essence, that XOR becomes a flip not flip based on whatever the data line is. So that's usually what you do is just add an XOR and you get a T flip flop. That's useful for like counters because usually when you're counting, something's constantly changing. So you can just send the T signal, which means keep counting and keep counting. So that's where they're typically used. Everybody know what a JK is? This is usually covered in your logic course. And we kind of like them, but they're, a lot of people forget them because they're specialized. What's the danger with an RS? Yeah, both of them, and I release them both at the same time. So we don't like the 1-1 state, right? What a JK does is say, what if I remove that 1-1 state and turn it into something useful? Because right now you've got a hold, you've got a set, you've got a reset. The only thing you're missing is flip. So what if I design some logic in front of it that turns an RS flip-flop into exactly the same as the RS flip-flop was, and then the 1-1 state, it becomes a flip the memory. Now you have all possibilities. So half of your input things are X's. So you have a lot of X's, which means you get to pick it when you do the encirclements. That gives you a lot of flexibility. So JK is designed for that. I'm doing a lot of logic, and I want to have a lot of options for what's happening. We tend not to do that for a asynchronous circuit because the extra logic just adds more time. And if you're doing async, you care about timing. But if you're doing timed logic, JK makes your life easier if you're dealing with specialized systems. You just get a lot of encirclement possibilities. Right? Just always keep them in the back of your head. Right? There's a reason for everything. Right? So we've got for our memory, we could have any one of those. They could be timed, they could be not timed. Now we want to consider this and think, what exactly is going to happen? How am I going to take this system and figure out if this works? What if I'm timing things? Do I have enough time to get it done? Things of that sort. So we're going to work on this. I'm going to assume that this is the way the signal flows. I'm going to have time kind of progressing. I'm going to presume a just because it gives me an easy event. If it's not clocked, then what you've got is some event happens, like the changing of the flip-flop or changing of the latch or whatever it is. There's still an event that happens. Now, this is really important to think about all of these things in terms of an event. The event could be the clock changing, the event could be an input changing, but we always have an event. How many people have programmed in either system Verilog, or VHDL? Most, right? A few people. So can anybody tell me what's the difference between a normal programming language and a hardware programming language?
To specify the sequence or combination of by default specify.
So believe it or not, that's an option we have, but we're actually like a regular programming language, you specify a sequence, right? So that's actually not the big difference. Both ones can be what's called sequential or procedural if you can use computer science. Like they have this procedural options. Right? Are we object oriented?
Yes.
Inside Verilog or VHDL or whatever. Yes, we are. Right? It's not as, like you're used to probably seeing a templated class or things like that, and that's an object. Most of the object hardware is pretty standard for us, so we hide it from you. Since it's, right, the constructor is always the same and stuff like that, so we don't make you build it. We just give it to you for free. We know exactly what needs to happen within the system, so it just automatically gets in. When you write a module, that's a class. Right? And it gets a whole bunch of implicit stuff. Now, when you normally make a class, in addition to constructors and destructors, you have to handle input and output stuff. Right? To us, it's very, very obvious what those inputs and outputs have to be. We can just look at a function description on that module, and you're going to tell it whether it's coming in, out, or it's in, out, it's bidirectional. So we can make all of those interface functions that allow you, to do gets and sets and all that kind of stuff. You get them for free because there's only one choice, right? But that's not what the big thing is, right? Typically now, if I was just in a computer science thing, which I build all those things, and then something changes and it just starts running, right? But to us, we're adding one extra real key feature. There are certain key events. So we're not just a programming language. We're what's called an event-driven programming language. Right? Events are a real key idea. This is exactly, a regular programming language can do event-driven. That's what a windowing operating system is. You have events like on-click, right? Release mouse, mouse over, we have a whole bunch of events. And so you can access those events and functions to handle it. When you get into VHDL or system there, you're gonna be dealing with events. Right? That input output automatically becomes your events list. Right? If you have anything that has an at sign after it in a command, you are specifying an event list to it. You're telling it what events are crucial. That's going to drive that function. All right, so, if we have like an always, and we have in that always, or if you're, going into system Verilog, you'll have, always combs, or always FFs, or flip-flops, or like always latch, right, things of this sort, right? If you have those, you're going to have an at sign, and you'll have a sensitivity list. That's the event list. There's only one function that can handle it, it's what you write inside that block. Okay? So the big thing to us is we simplify a lot of that class routine and we give you an event list. Like you're building logic from that. It's going to, from the code you write, and there doesn't actually have to be any procedural. It could all be objects. Right? So that's what I'm saying. Procedural is an option to us. It's often an easy option, but it's an option. When you are writing that code, it's going to try to infer what the logic is. Right? So when you went through your digital logic course, they should have started giving you an introduction to what type of hardware corresponds to what command in a language. That may seem like an odd statement. Some of them are kind of obvious, right? If I do an and or an or, you obviously know it corresponds to the gate in an and or an or. But for instance, if I were to do a simple statement on here, like, A equals B plus C, what does that correspond to hardware-wise? I need hardware to build this, right? So we have to think about this because we have to realize how to time them, right? When I get a command, what does it build hardware-wise? How long does that hardware take to do something? That's what we're trying to ask here, right? So when you see something like this, right? Obviously, if I had something that was like, A equals B and C, you would have this problem. You put an A, right? This would correspond to, here's B, here's C, here's my AND gate, there's A. Easy enough to infer it is. How about this one? If it was, right? But that's not, right? That's literally addition because to us, right? Remember, there was a lot of options for and. It could be the dot. When you go to any program, I don't care whether it's system Verilog, I don't care if it's VHDL, I don't care if it's C++, right? All of them, all programming languages follow this convention. Even Fortran has it, and Fortran goes back to the 1950s. Okay? No matter how old your language is, the convention stands. Ampersand is for ands, and a verbal pipe is for. And you could have one or two of them. What's the difference? No, where's the bitwise? Very good. All right, so you make my digital logic heart happy. Right? Right? So which one's which? Double ampersand is logical or bitwise. That's logical, right? Single is therefore bitwise. What's the difference?
bit instead of check. So
Yeah, it just treats the entire variable as one thing. In most cases, when people are doing the double one, right? Generally, if you have multiple bits, it's whole bunch of zeros is zero, and a whole bunch of zeros and a one is true, and the other ones are not. That's the most common definition. There is one slight variation, which is all ones is a one, right? This one is actually what Microsoft does in its programming languages. I have to make this as a special, because normally I despise Microsoft, but they're actually right. That's pains my heart to say. I have a bunch of my former students who work at Microsoft, so, but it's just, they normally do so many stupid things. But in this case, they did the right thing. If I do the way that most people do, where it's all zeros and a single one, and I get a single event upset, and it flips that first hit, I have no way to recover. If I'm using all of them as ones, and I get a single event upset, cosmic ray hits, radiation hits, electromagnetic pulse, whatever else, it flips some of the bits, I have a chance to recover those multiple bits. Because I can do all of them and take the most, right? Then I've got some protection, which I don't have yet. Anyway, that's a side note. So logical only checks, there's only two possible states. Bitwise does them all, so you're in essence building a whole bunch of gates when you do bitwise. Almost always we want bitwise when we're building hardware. Almost always you want logical when you're programming. That's why you probably only thought there was the double stand if you only dealt with C, C++, Java, whatever. They always do the double one. It's actually the other one that's built in, but it's almost never what you want because it's usually the condition in an if statement that you want true or false. And so you almost always mean logical in those cases. Bitwise is pretty much always what we want. If you're building hardware, there is a small chance you could be doing a logical test, in which case you do need logical in that case. Right? If it's the condition of an if statement, you probably do want logical at that point. Okay? But in most cases, if you're just trying to build something and do something on it, then you probably need bitwise. So that's kind of some general rules on this. But anyway, you can get this. What is this? Can I look at addition, or multiplication, and infer a circuit? Yeah. What is that circuit? In this case, it's adder. It's not OR. Because OR is that special, it only does OR. So, 1 is 1, but 1 plus 1 is 2. Okay? So it is a different situation. We have a symbol for an adder, and we're actually going to, in a week or so, start looking at some of these circuits that we have to build and look for better ones. We'll do a barrel shifter first. We're going to look at a couple different forms of doing arithmetic. You've probably seen Ripple ones. We're going to look at conditional sum, and we'll talk about some other functions. And it takes some special constructs to build them, but they're faster and have a lot of improvements. Right? So, right, what if you want really fast arithmetic? Well, we're going to talk about what are some of the trade-offs that go on. But for instance, this general symbol, if I don't write anything in it, is an arithmetic logic unit. Right? And in this case, I've got B or C coming in and A comes out. If I put the plus in there, it tells you it is a specialized arithmetic logic unit called an adder. Which just is an arithmetic logic unit that can only do addition. So that is completely inferable. We know what those design means. We can make libraries with them in it, right? Things of that sort. No, it can infer them and go on. Right? What if I get to something weird like, if A, then, whatever, B equals C, else B equals not C. Is there a hardware equivalent to this? It's a mux. Really good. Exactly. This is a mux, right? So if you think about this, this is a two input mux, 0, 1. This is my true false condition. This is A right here, right? And if A is true, then the 1 happens. Well, in that case, B gets the value of C, right? Else, then A is 0, B gets not C. But an if statement is understandable as a mux. So you can start to see, I can actually take your program code, even control commands like this, I can start saying what is the equivalent piece of hardware and how do I cascade them together. This is what Verilog, VHDL does for you. It's going to go through and it's going to look at these commands and the sequence of them. It's going to figure out, oh, the earlier ones cascade into the later ones. And so it can actually build a circuit in pieces from your commands. Does that make sense? So whatever you're reading your programming language has to go this way. Now, can you imagine there are potentially some constructs that are harder to tell exactly what's meant? Yeah. Right? So what I want you to do, if you're going to be a good hardware designer, you should think about how can I make it easy for it to infer what I want it to do. Okay? It's going to infer something. If it infers what you don't want to do, it's going to do what it thinks. Okay? And those circumstances, it'll build the wrong circuit. And you may use stupid programming language, but in the end, it's always a stupid machine and programming language. It's your job to get it to do the right thing. It's still your fault, even if it's the one that does it wrong. You know, maybe it's fault, it's your problem. You should have known, right? Imagine if you were talking to one of, a friend of yours who is not necessarily the sharpest tool in the box or whatever you want to consider it, right? You got to be careful in what you tell them to do because they could run off half-cocked and do something dumb and say you did it, and then everybody's going to stare at you, right? So when you're dealing with those cases, you're really careful at what you say. That the computer is your dumbest, most run after it friend you have ever imagined. Okay? It will completely do the stupid thing. So you have to think, what is it building? And make sure you write your code so it can't get confused. Otherwise, it builds the wrong thing and you get garbage. Does that make sense? Okay. On the bright side, it's going to do a lot of work for you. So this is a little bit of a notational thing for us, right? That programs are equivalent to our hardware. Okay, and it's going to turn your program into it. When we talk about timing your design, we don't mean timing how long your code takes to run. Right? We mean timing how long the implied circuit will take to do something. Because we don't care about the code for which it's going to infer the thing from, we care about what it actually builds. Right? Computer science people want to time their code, we want to time what the code implies. Right? It's all about what is the user going to use. Okay, so remember, these ones are going to come from some set of programming things and they will build it. So we know what the hardware is, we can now come in here. We know it's event driven, so some event's going to trigger it. At the moment, I said, let's assume we are synchronous, which means I've got a clock coming into my memory, right? And that clock is going to be a timing reference. Now, I have to get a little more involved in how this system works than we have before. It'll be based on it, but you have to understand a couple of the parameters. So if you ever look at a spec sheet on memory or combinational logic, they'll give you a lot of stuff. They'll give you sample circuits, they'll give you performance behaviors, they'll give you voltage ranges. They'll also give you a ton of timing parameters. And so I want you to learn what a couple of these terms mean so you can read those fact sheets and get what you need. On the bright side, if you mention what the logic is, and you do this inside of a good programming language like Verilog or ADL10, it's got access to all those logic families, which means it's got all the spec sheet data in it correctly assigned. So it will correctly pull in the data so it can time things. If you ever wondered why you're programming these things, why you had to say what system you were on, and even more than just that, you had to give versions of that system, it's because he wants to get the correct timing data, the correct programming data. There's a lot of information it's going to pull off of this. One of which is this. So let's talk a little bit about memory. So let's say I had a flip-flop, and I'm going to take my flip-flop, and I'm going to draw it maybe a little different than you're used to seeing it. That was not the best draw on my part. Oh well. All right. Reset, set. I imagine I have a flip-flop like this. I should have done that one to the top so I didn't have a cross, but oh well. I don't claim to be the prettiest drawer. So let's say I've got a flip-flop like this. Realize this is identical to putting them next to each other and having the crosses. The advantage to this is you can see that it takes two gates. My worst timing, right? My best timing, I go, from one thing to an output, the other one two. Right? So it can take up to 2 gates worth of logic to get there. Now, on top of it, there's extra logic that goes in front of this to actually turn it into a flip-flop and get edge timing. We could have 2 or even 3 interlinked flip-flops depending on the style of edge transition we're going for. But in our case, I do have a timing signal, and you want to think about the timing across this loop. Well, what would happen if I set my values, whatever, reset is 0, set is 1. All right, so I'm trying to set the output to be true. Right? Now, in the midst of trying to set my output to be true, right, I run into something where, let's say, partway through this, reset turns on for a brief bit. All right, so there's a change. And maybe it goes on for a bit and then off. Right, just a glitch comes through. I'm trying to clock this, so I want glitches to go through. During this time, it goes to the bit. If there's enough time, who cares? It'll get cleared out, right, as it cycles around. What if there's not enough time? Yeah, things are unstable for a bit. So I want to prevent that. So I'm going to want a period where set and reset my inputs cannot change within that clock cycle. Because otherwise, you can imagine what if I go to 0, 1, right? So I'm starting to set the thing, and then set turns off. Well, I started to transition and now it turned off. Does it make it up and latch or does it drop back down? Well, it depends on how far you progress. Well, how far do you progress? Well, that depends on how hot it is. Right in the logic family. And it's starting to get annoying. What if it gets to the middle and it gets stuck? Right? Because I turned it off partway. Now it's become metastable. And you don't know when that dumb thing's coming off. See what I'm saying? Right? There's a lot of things, even though I'm avoiding the whole 1-1 problem in disconnecting, I can hit metastable by not giving stable inputs, right? If I'm, just going like crazy, flipping things, I can do all kinds of weird stuff that who knows. You just always have to be careful. When we've been assuming this, we've been assuming that the inputs are coming in an organized fashion. What if they're not? And I always caution you, think about the craziness. I often call this the English major check. And the reason I call it that, right, nothing against English majors, but my roommate in college was an English major. And so whenever I needed to check some of my circuits if something bad could happen, I handed it to him before I turned it in, and he would do everything imaginable that I could never think of. If you ever wonder why the end users get weird results, it's because they do what my roommate did. And he would smack it, and he would shake the thing, and he'd just start flipping them on and try to push them halfway. He'd have all kinds of fun to see if he could screw up this thing, which I loved. Because I would never do that type of stupid stuff. But he's doing some of the weirdest reactions, and that's what this is. So you always want to be cautious of those. So we would want to protect these. Well, we make a requirement. Imagine this is when the clock hits, right? Again, we're doing a timing. So let's say the event hits part way. Maybe I'll just draw it as a timeline and then I'll show you here. Right? Let's say the clock hits right here. This is my clock's positive edge. At this period, I want my inputs, set and reset or whatever else, I want them to be stable for a little time period before, and I want them to be stable for a little time period after. Make sense? This is my safety margin. I don't want my roommate to be right during that, because otherwise I could do exactly what we said. It starts getting up there and he turns it back off again. Right? And it gets stuck in the middle and who knows where it goes. Right? Or maybe he does it a little bit slower and it fully latches, or he does it shorter and it doesn't latch. And you can imagine all kinds of craziness going on. We give names to these. This is called setup. This is called hold. You will find all over the place, there'll be things like T clock. I always did this. Imagine that's a CLK. So I should have glasses on, make sure I don't write things badly. Now there is a little bit of a gap there. Okay, time CLK, right? Time for the clock. That's when this puts, right? The time of the clock is saying, I get information about my clock pulse train. And if I'm doing positive edge, time of the clock specifies how long I've got between these. So implicitly, this is telling me when things are happening between each one. If I was doing pause edge of clock, for each one of these, there's a safety margin that I want to put around it, right? Which is what these are. I need a little setup time. I need a little hold time. We usually call these appropriately TS or T setup and TH or T hold. There. That's a little protection over here. Okay. And this can be different for different logic families. Right? Some logic families, they are only concerned with the setup time, and once it has right, hold isn't really required. So you might find T hold equals 0. Okay? Sometimes they use their stability factors, and they make T hold have some time, and T set is really small. More often than not, P setup will be non-zero, and P hold will either be something small or zero, which is actually due to another thing we're going to be in a few seconds here. It can be both. Older families have both. It's kind of true to life. Newer families tend to put more emphasis on hold, so on setup than hold, the time before. Okay? And that's just kind of on each one, when you see that. Now, when you consider this, I consider here, I've got setup and hold around it. I've also got, right, a setup and hold on the next one. So if I consider between two time periods, I get the hold at the front, I get the setup at the end. And then in between, this is when you can do all of your logic. Because on here, this is my when T clock happens, my time is going this way, so I have setup before, and I have hold after. But you still have to go through this whole thing to get the next calculation gone, to get to that next setup instant. Does that make sense? So if you were to look at this little period here, from here to here, right, that T clock, I keep doing that, T clock has to be bigger than my T hold plus T setup plus this in between here is everything else. We'll fill this in a sec, but I just want you to get the idea. Right? All the rest of the things that are going on has to happen in there. Your clock speed, if it is not bigger than this, there's not enough time to finish it to safely store the result. Therefore, you could be unprotected. So remember, we're doing this timing to make sure we sample only at the right points. This is seeing, can I actually get to that point? Is my timing really fitting? If T clock is shorter and shorter such that it doesn't have time to finish all these, then you are not protected. This calculation is done for you automatically for every possible register-to-register combination inside that FPGA when you tell it to do your synthesis runs. So if you ever wonder why it's taking so long to do that, it literally has to time every wire to figure out what's going on. This is part of what's going on behind there. And it tries moving things around to make sure that it meets your timing requirements. So when you start thinking what it's really doing, it becomes more and more impressive that it's doing that on a standard desktop system in, a minute or two. So give it a little respect when it's going through that. And some of that is, some other aspects as well, but this is one of the big areas that it will sometimes come back to you and tell you, I couldn't get it this. So if it's stopped short and it tells you something about some critical time or something like that, or it doesn't fit, it's warning you, I wasn't able to make this work. It is possible some things can be so far away that it just takes too long to do the updates. You can often rearrange your code a little bit, rewrite it, which will force it to rearrange the system, and it might find a solution to that. So understanding what's happening in here, even though you will not be doing these calculations, at least let you know what is the problem, right? And you generally want to fix that by rearranging. Sometimes breaking things up in pieces, stuff like that. Does that make sense as a general? Okay. So let's talk then about what we can do with these, right? Now we have some idea here. Let me add that one extra little provision I said about the T-hold. Take a look at my circuit, right? How long does it take, right? Because usually before this, right, if I was looking at it, the simplest design that I can do for, some type of a flip-flop area to get an edge transition is I pass things through and I have an inverted clock. And let's just say I'm doing a D flip-flop, whatever, right? So if the clock is high, it'll let it go through here. But if it's high, it won't let it go through here. The second the clock turns low, this one turns off, that one turns on, so so that's an edge sync. In this particular case, that's a negative edge. Flip the inversion on, you get a positive edge. This is the simplest edge triggering flip-flop you can build. It is not the best, but it is the simplest one you can build, and it illustrates my issue. From when the clock changes, right, to when a new piece of data is available will depend, right, from my clock transition, right? There's two different flip-flops, things have to pass out. This is the final output queue. How long does it take from a clock transition to when that data is available in the queue? Well, in this case, it's got to go through two flip-flops. Depending on your circuit, it could be more, cycles, this fun stuff. So we can actually, that's important though, because we're often doing this type of a thing. Here's your input, there's your output. This is D, that's Q. A clock comes in. I want to know how long it's going to take till it's available from the inputs to the outputs. That's what T, the time for clock Q is, right? We often call this time here how long across the whole thing, right? And it only lets you in here, so we'll do something like clock, You'll see it written this way, clock arrow Q, clock to Q. You'll see this written as a shortcut that's like clock the number 2, Q. Sometimes they'll put a T there. Right, clock TQ, meaning QQ. There's a lot, depending on the thing, they'll give it a lot of different names, but that's what it means. How long does it take once the clock hits for the inputs to become available on the outputs, the change to have settled? Right, now that is technically covering across, in some sense, it's across the whole thing. But we often, since we're measuring it from when the clock hit, it overlaps hold. The hold means how long do you have to keep it till it's stable. Clock to Q tells you when is the data first available. So usually clock to Q is a little bit longer than T hold. So typically you will just report T clock to Q in your testing area while I'm doing this. Since they overlap each other, right, I'm just going to do an abbreviation, C to Q, clock to Q. Right, clock to Q and hold overlap each other. Clock to Q is usually bigger, so oftentimes we will just dump hold and replace it. There are a few cases where they vary. You might get the signal early, but if somebody drops the input, it might not hold. But you get the data very early on, in which case T hold is longer than T clock to Q. So sometimes you'll do max T hold or clock to Q, right? Whichever is bigger, getting that one. In some cases, people measure from when the hold is done, how much longer till your data is available to you. In which case you do T hold plus T clock to Q. Which you're probably this one going, well, which one is it? Well, unfortunately, it depends on your family. So you have to look up in the data sheet and do that. Or you do a programming language and you tell it what the logic family is. In which case it's got the spreadsheet and it does it for you. Right? Most of you are not going to want to do this on your own, which means just let the logic family do it. But you should know what's happening. And if you have to read the sheet and you get some weird behavior, there are times when somebody enters the data. I've encountered it, it calculates it wrong, and you're like, what the hell's going on? You have to know where, now you can go back to the spreadsheet. It's going to be one of these things, look it up. Somebody probably didn't think about it, did the standard, which is, picking T clock to Q, that's the most common, because it's usually much bigger. They just entered that one, they ignored the rest, but the logic family specified it some way. Right? More and more new logic families are just zeroing T hold and then just specifying clock to Q, and they just do that max for you so that you're always just getting the read state value. Which is why I mentioned newer ones tend to ignore hold and make it zero. It's not that it's actually zero, they're forcing you to just get clock to Q and pick the safer number, whatever's bigger. Does that make sense? Unfortunately, there is no set rule because there are tons of companies, and in the past, people put in often the more accurate information, which is to give you both, and you figure it out. But they've been moving more and more to the safety thing. Does this make sense? Okay. All right. Now, we've talked, and this is the most complicated part. There's actually one more bit of this we'll have to deal with, but I need to introduce the rest of this first because it's all part of this T everything. All right, we've got this. We know the time across it. What's the rest of the things I have to consider for timing in this diagram? Very good. Okay, the wiring. We're actually going to say there's two different wires. Sometimes they lump them together, sometimes not. Because light is slow. And that's the best you're ever going to be able to pass your signal down the line. It actually won't even be that good. But the best you could ever hope for is light. And people are probably wondering, what do you mean light is slow? What is the speed of a typical computer? A good desktop. Yeah, you can buy different ones, but about what you're talking. 3 gigahertz, 2 gigahertz, somewhere in that range. Right? 3 gigahertz is usually, 3 and some change. It's normally your upper limit. That upper limit has come in since 2003. It's been stuck.
Yeah.
And it's been stuck because
It's been stuck because of the transfer.
air cooling. It's the air cooling limit. That's how fast you can flip them and still get rid of the heat off these things. Right? If you go to liquid cooling, you can move up. But generally speaking, it's 3 gigahertz, somewhere in that ballpark range. Right? How long of a time period for 3 gigahertz? How does frequency relate to that? 1 gigahertz is my frequency and time is 1 hour. Okay? 0.3, a third of a nanosecond. 1 gigahertz is 1 nanosecond. So we're dealing with a third of a nanosecond. How far does light travel in a nanosecond?
10 seconds.
And so we're running about 11 and some change inches. We'll run about plus. Okay? There's a little bit less than a foot in a nanosecond. We're dealing with a third of a nanosecond. So how far does light travel for your typical desktop machine? Less than 4 inches. So in terms of your clock, think of light leaving those tubes at the top and hitting the floor. Fine? We got what, maybe 10 feet? So it's 30 cycles of your clock for light to go from the bulb to the floor. It's a little bit, it's kind of shocking if you think about it, right? Because we don't realize timing really matters. Timing all these wires is non-trivial, okay? So we call this the time of flight. Like an aerial flight. In our case, it's the signal going down the wire. So you will see time of flight. It's sometimes abbreviated as TOF, right? Time of flight. You'll also see TF for time flight, right? This is just how long it takes to propagate that network. The best it could ever be is light speed, which would depend on the length.
We'll have that.
Yeah, so, but it's not going to be.
Which is cover that in cover, or the cover call it.
Exactly.
Pretty slower than the speed of light.
But it's not just that. Now you have to deal with the permittivity and permeability that's going on, right, which is going to change things. But even more so on that, you probably have an effective RC circuit. You have wires near each other, which is going to provide some capacitance between them. There's resistance down the wire and things like that. So this is even slower than that is. So this is your real limit, is going to be the RC constant of what the material is. This is why material choices and how you are building your circuit is so darn important. Because the time for the signal to go down the wire is heavily dependent on how that thing is laid out in its material properties. So, and if I have just one time constant, RC, right, and you're going to get C from the capacitors that are within this and between wires and all kinds of stuff. So there's some net capacity, some resistance down the wire, right? How much does one time constant allow the signal to change? So if I consider just, I'm rapidly running out of room there. Here's time, right? And I'm considering just a simple RC circuit, right? That's been, it's got a classic switch here, right? And then I've got a resistor and a capacitor, and it's coming back, and here's RC. So when the switch closes, it's going to go through this lovely thing, and you get a response that looks like this, right? First order response right now, just have RC. So you're going to get this lovely response. What's the time constant tell me? Technically, this thing never hits its value, right? But we're engineers, at a certain point it gets close enough. What does the time constant tell me? to get to what amount? No. Yeah. It's like that, because technically speaking, right, here's my max, it actually approaches it asymptotically, it doesn't hit, right? So, and like I said, we practically get close enough, but a time constant doesn't actually cover that. It's actually related to E, right? So you're looking, it's E to the time over RC, that's what's charging up. In essence, it's technically 1 minus E to the minus T over RC. But, it's basically related to that. So one time constant gets you to that natural log value, which is 0.63 approximately. And that's tau, our time constant, which is RC. Right? So it gets you to 63% of your goal, basically. And then what's left over, the remaining 37, in the next time constant, you get to 63% of 37. Right? Added on to it. Right? Which is why you can keep going out with time constants and it gets smaller and smaller. At what point is it good enough? We usually say 4 is good enough to be close enough. That's a heuristic, but it works pretty well. But it'll depend on your system. Some people count what's called 1090 time. Right? We consider 10% of the voltage swing is considered a 0 at the beginning. Anything above 90 is 1. Anything in between is potentially metastable, and please don't stop here. Right? So we say our change ranges are 1090. That's a fairly typical one because I don't know anybody who has a problem latching, below 10% or above 90%. But you could have better, right? Actually, if you think about it, an awful lot of our systems latch below 1 volt and latch above 4 volts on a 5-volt scale. So technically that's 2080, right? But you're going to have some number of these that's going to matter. How strong does it have to get? That's going to depend on your system. Sometimes we don't just do this, we try to critically dampen, we could do all kinds of things. We could try to get it faster by doing overshoot, but then you get oscillations, settling time. Right, so there's a lot of ways we can try to speed this up. In essence, whatever they do in your logic family, they have to give you some idea of what those distances are and what it will take to launch. Generally speaking, that's particularly when you're doing with an FPGA, that wire is probably crazy, right? If you've got, consider this as your FPGA's area that's on, I could be coming from a flip-flop here and going to one here, but it might be routed through some crazy type of route because I don't have any, I have to follow available wires with other region competing for the space. So I don't necessarily get a straight route. This is why this is not possible for a human to calculate in some sense. Right? We often are going to have to actually, let the system calculate it because it's going to reroute the wires, and when it reroutes it, it's a new timing, then it's got to update all the timing charts to see if it works. That's what it's doing when it's doing all those routings. It's trying these different things and saying, what's my timing? And it adds it up in little units because it knows the time constant, how long does it take for that to work, and it can just add them all up. Does that make sense? If you had to do this on your own, hopefully you would wire it more straight. Right? Like if you were, because you're not going to do this for an FPGA. If you were building a physical system and maybe you actually explicitly built wires, you would actually put the wires there. Right? Anybody who do the physical digital logic labs? You ever sometimes put really stupidly long wires and you sometimes get bad behavior? Now you're starting to see why. Plus, as you make a really long wire and they start interweaving with other ones, guess what happens? You get mutual inductance, you get cross coupling, and now all of a sudden one signal turns on and you get a little kick. Right? All of these things happen and have to be checked on a good circuit design. Alright, so just because we're in digital land, I don't tell Charlie this, we still have to deal with analog effects, right? But we never want to admit that in front of an analog. person. All right, we feel good with this. So this is what we call our time of flight. Okay. So for our everything, when we're considering this, T everything, I'm just going to put ET everything. We know it's time of flight, but I potentially have one, two of them. So I could have two times the time of flight. On an FPGA, you only have one, though. And that's usually because the combinational lookup block and the memory is often in the same block. So usually once you have calculated the logic, the flip-flop is right after it, so there's appreciably no link because they're in the same little memory cell. There are some cases if you go to an external RAM where it could be. There. So often it's either time of flight or two times time of flight, depending on whether you have. If this one's really short, we ignore it. That takes care of this, and we've talked about mostly memory. The only thing left is combinational. This we often handle as a number of gates. This is why we like two logic gates through, things like that. We don't want too many logic gates. Your worst timing in number of gates from the input to the output is going to affect that timing. So let me go back to my original one where I had that little adder there. The first logical adder you build, right, when you go to NASDAQ, is going to be a ripple carry adder. Right? What's the timing of a ripple carry adder? Anybody remember? It's a minimum of 2 gates per bit. Right? So now if I've got a 64-bit number, you're talking 128 gates. That's how long it would take for the least significant bit to propagate to the most significant bit. Now, often your most significant bits, many of them are 0, right? Because 2 to the 64th is a stupidly large number, right? But technically speaking, it could happen. Does that make sense? Therefore, we don't want, for large modern systems, we don't want to use a ripple curly adder. That's why in a few weeks we're going to look at conditional sum. Instead of it being linear in time, it's going to be logarithmic. Right? So log base 2 of 64 is what? 6. Right? So to go from 128 gates to 6 to 12 gates, good? Yeah, significant improvement. Right? There are also ones that are truly linear, but what happens is time-space complexity trade-off. The number of wires needed to go into a gate for a ripple carry adder is constant. Right? You only ever need 2 wires to get into those gates. If you go to our conditional sum, it'll get up to log 2 of the number of bits going into the gates. So that still puts me in 6 to 8. That's a reasonable range for most logic to handle. If I go to the really super fast ones, right, carry look-ahead adders, right, that can do things in 2 to 3 logic gates total, no matter how many bits. The number of input wires per gate becomes linear to the number of bits. You now need AND gates with 128 wires coming into them. Right? This becomes impractical for choice. So trade-offs. Now, could I build such a thing? I could. Right? But it just becomes complex, right? Now I got to figure out which is worse, time or space problems. Time. Good? Yeah.
Okay. The block time is faster, takes more space.
It takes, yeah, because more wires are going into each gate, and more wires into each gate means more current, more heat, more things like this. Right? So that's commensurate. There is always a trade-off in engineering. and you pick the one that fits. The key thing for us is I know about how long each gate takes, so I can time in the logic family what a gate is. I find out how many gates to make it through. Now I can get what the time is of the combinational logic, which we call T comb. It's based on my how I build a particular item and what the logic family for that is. Right? So, implementation style and everything else matters, right? A lookup table never actually builds all the complexity, it just stores each individual result. So it is always pretty darn fast, but it becomes huge in the memory required to build it. Life is a giant trade-off, right? What do you want to achieve? Again, it's a times-based trade-off. Speed versus size, area of the disk or area of the silicon that I'm building. Right now, you don't have to perfectly see, you just have to understand there is a trade-off and where the time is.
So, generally speaking, we make a rule of like the larger the combination logic, but faster, or
Always,
no.
but generally, if I make it faster, it will probably become, if I'm reducing latency, it will probably become bigger to allow me to do it. Because I have to pre-calculate stuff and all kinds of other things. I have to do specialty things to get it. You can make it big and it's slower, right? But if I take a good design and I want to make it faster, I almost always have to add extra stuff to speed it up. So a good design sped up will usually become bigger and require more power. That is general. And there are exceptions, but it's, a general. That's general. Does all this make sense? So when I'm doing the comparisons, my everything, I have to take the time of flight and the combination. Oh, there's one other thing, let me just mention real quick. It's called T-skew. Right? Right now, everything we've done is telling you how to go to this particular launch here. I'm starting at a register and coming back to that register. In reality, when you're dealing with a system, you might start in this one and end it here, and maybe the combinational logic was here, right? You're not starting and stopping at the same one. Well, it takes time for your clock to propagate. Not every area of your chip sees it simultaneously. It's emitted from one location and it's got propagate. If you're closer to the clock, there's no skew. Skew is how much the clock has been shifted because it's further away. Right? If you're really far away, it takes a little while before you see the clock. And the original clock has changed in that time. So that timing it takes for the signal to get to you is called T-skew. This is why clocks have their own network layer inside an FPGA. This is why you cannot build a logic circuit to act as a clock. Because normal things have to be routed in this stupid way. If we make a clock layer, I can make it really fast and you just go the shortest time. Right? There's no problem moving, it just gets there as fast as I possibly can. Right? That allows me to prevent that, so I can time precisely. If you're going through the logic layer, right now my clock even follows some stupid route. That's really tough to calculate. So we just disallow that. So FPGAs will never allow you to clone off of a logic signal. And if you force it to, it's going to build separate logic that you can't send the clock there. And in essence, your whole system will time that. If you ever try this, you'll get flickering and all kinds of other bad behavior. Because he doesn't want to do that. It's against the rules. All right? Because it's just too hard. Does this make sense? Timing issues? Right? Just make sure you follow the time, each of these, right? My everything. So technically your final thing is going to look like the time of the clock has to be bigger than whichever is worse of these, plus the setup time, plus the time of flight could be doubled, right? Plus however long the combinational logic takes, plus how much the possible skew of your clock is. If your clock is not long enough to account for that, you can get glitches and it'll flag you with an error. You either have to slow the clock down to get a bigger timing, or you have to speed up your circuit. That's life. Good. Awesome. That is the basics of timing. If you got questions, as always, come up, and I am happy to answer. So, stop this so you don't have to be recorded.